Okay, so we shall start this week's lecture. So, good evening, everyone. This is Anand Singhal, PhD student from IIT Jodhpur, and I'll be assisting you in solving the tutorial problem for this week, which will help you in solving the weekly assignment that you have been given. So, till now, what we have covered. So, today, what we'll do is we'll end the combination circuit part of this course. You all might be having the exam of your course, maybe mid-exam. So, that will cover this combinational part. So, till now, what we have done is we have covered all the types of combinational circuit. We have covered this Boolean algebra. Okay, let me. Yeah, so in the first week, we have covered basic diode circuits. Let me give me a minute. There is some problem with the pencil. Give me a moment. Okay, so yeah, there's some problem with the pencil, so I'll try to solve the questions manually by just telling you the answer. So, again, welcome to the course. So, in this week, what we'll cover is we'll end up the combinational circuit part, which we have covered is the introduction and the Boolean algebra first, all the K maps and SOP POS, and then in the week three, we have done the minimization part by different types of algorithm that we have and different type of hazards. Then we have covered few combination circuits such as multiplexers, demultiplexers, etc. And then in the last week, we covered the basics of the number systems. And in this week, we'll end the combination circuit by few more circuits, which are comparators, look-ahead adders, and some error detecting and correcting codes. So we shall start. So here's the first problem. So what is given in this problem is uh, it has been asked that the output F1, F2, and F3, what will be the output F1, F2, and F3 such that x equals to 0 and y equals to 1. So this is quite a basic problem that we'll cover. Okay. So as you can see this question, what is F1? F1 is nothing but when x and y are XOR, we are using a NAND gate for first. So X and Y NAND, and then again this X and Y NAND is NAND with the Y, and then again it has been inverted. So this circuit is nothing but a 2-bit magnitude comparator where F1 produces the bit when Y is greater than X, and F2 produces the bit when Y is less than X, and F3 produces the bit when y is equals to x. So this is a basic circuit of a magnitude comparator, uh, that a 2-bit magnitude comparator that will cover all the three types of possibilities. So a 3-bit magnitude comparator is nothing but either y will be greater than x, either y will be less than x, and either y will be equals to x. So I'll repeat again. So F1 is what is F1 is doing? It is completing the circuit when y is greater than x. And then F2 is using the circuit when y is less than x, and then uh, F3 is using the circuit when y is nothing but equals to x. So in this question, it has been asked that when x equals to 0 and y equals to 1, so what will be the output of the circuit? So you can see when y is greater than x, then I just said that F1 is representing that circuit. So for that, F2 and F3 should be 0 and F1 should be 1. Then only this circuit will work because F1 is a condition when y is greater than y is greater than that of x. So a 2-bit magnitude comparator will work when F2 and F3 will be 0 and F1 will be 1. So the answer to this question will be nothing but option number A. So I'm having some problem in using the pen. So I'm trying to solve the questions by most of the questions by speaking, and maybe you can try by your end. So the expression, some of the expression will come for F1, F2, and F3. So you can check by yourself. So F1 will give the expression when y is greater than x. F2 will give the expression when y is less than x. And then F3 will give the expression which is nothing but when y is equals to x. So the correct answer to this question is option number A. Okay. We'll start the next question in 2 minutes. Okay, so sorry for the glitch. I'll try to cover the question by writing now. Yeah. So as I said that F1 will cover nothing but when y is greater than x. F3 will cover when y is equals to x, and F2 will cover when y is less than x. In the question, it is given that x is 0 and y is 1, which is nothing but when y is greater than x. So for this, what we want is our F2 should be 1 and rest of the terminal should be 0. So this circuit is nothing but a magnitude comparator. So the correct answer to this question is option number A. I hope it is clear. And sorry for the glitch. It took some time to resolve it. We can proceed to the next question now. So it is a theoretical question. It says that which of the following statements is or are false? You need to be careful. It can be true or false here. So you need to read the question carefully to answer the question. To answer the question. So the first statement is gray code is a sequential code. The second statement says in ASCII code A is represented by this thing and small a is represented by this thing. Then it says the for XS3 code the allowed values are from 0011 to 1100. And then the last option is binary to gray as well as gray to binary code conversion use only XNOR gates. So if we know the basics of gray code, we know that yes, it is a sequential circuit. So this option is not incorrect. So it is correct option. So it is a correct option. In ASCII code, we represent A by this quantity only when first and last bit are 1 and all the rest of the bits are 0 and we represent small a by this binary code. So this is also correct. Then for XS3, we know that XS3 starts with the 0 starts with a 3. So it is nothing but 0011 and it ends with the 1100 which is nothing but 12. So its 9 is 12, so this is nothing but plus 3 plus 3. So this option is also correct. Now it says that binary to gray as well as gray to binary code conversion use XNOR gates. So this is the wrong part. It always uses XOR gates. You might have done some gray to binary and binary to gray conversion in your last tutorial lectures. So they always uses XOR gates, not XNOR gates. So option 4 is wrong, which is the correct answer because it's the question says which of the following statements are false. So the correct answer to this question is option number D. Again, this was quite a simple problem. I'll repeat the first question again. So in this question, it was asked that what will be the value of F1, F2, F3 when x equals to 0 and y equals to 1. So this circuit is nothing but a magnitude comparator. It compares by whether y is greater than x or equals to x or less than x. So F1 covers the case when y is greater than x, F2 covers the case when y is less than x, and F3 covers the case when y is equals to x. So according to the question, answer to this question was option number A. And then we covered again a theoretical question. So let's move ahead to the next question. Yeah, it is quite interesting. So yeah, let's give it some time. Yeah. So now if you read carefully, so this is a ALU block. It says the engineer has selected the following logic. So if s equals to 0, what engineer has selected? Y0 is nothing but, so I'm using the for first part, I'm using this color pen. Y is not is nothing but a b bar, and when s equals to 1, so I'll use some other part. This y1 is nothing but a plus b whole bar. So to solve the first problem, which is for the first part, what we'll do is when s equals to 0 and s equals to 1, we'll cover the y naught first. So I'll write y naught is equals to when s equals to 0, that is s bar, y naught is nothing but ab whole bar. And then when s equals to 1, which is s, y1 is nothing but, uh, sorry, y0 is nothing but a a bar b plus a b bar. So let me try to open it. So it is nothing but s bar, this is a bar plus b bar, and then plus s, this is a bar b plus a b bar. So s bar a bar, I'm just opening the brackets, s bar b bar, then s a bar b plus s a b bar. Now if I try to take y0, yeah. So if I try to take maybe a bar common from this, so it will be nothing but s bar plus sb, and when I try to take b bar common, it will be nothing but s bar plus sb bar. So we know the major property, which is nothing but a plus a bar b is nothing but a plus b. So using this property, what we can write is a bar s bar plus b, since s bar is here and the complement of this is present here, and then b bar s bar plus b bar. So I'm again trying to open it. The final expression when y naught is for y naught will be nothing but s bar a bar plus uh, a bar b plus s bar b bar plus, okay, let me recollect. This will be a, and b take b bar final. This will be s a, yeah. This will be a. So this will be a b bar. So y naught, final y naught will be nothing but s bar a bar plus s bar b bar, and then a bar b, and then a b bar. Similarly, now we'll calculate for y1. So if I use some different ink now, so y1 will be nothing but for s bar, it is given that when s equals to 0, y1 is a plus b whole bar. And when s equals to 1, y1 is nothing but ab. So if I just try to simplify it, a plus b whole bar is nothing but a bar into b bar. And then this is sab. So which is present in one of the options. So y1 is, the final answer to y1 is s bar a bar b bar plus sab, and then y naught is nothing but s bar a bar. So we'll check s bar a bar is there, s bar b bar is there, then a bar b is there, and then a b bar is there. Yeah. So the correct answer to this question is option number C. I hope you understood it. So I'll repeat the question. So it this question has a ALU block which says that when s equals to 0, y naught will be this, and y1 will be this, and when s1 equals to when s equals to 1, y naught will be this, and y1 will be this. So we need to calculate y naught and y1. So for y naught, there are two possibilities. When s equals to 0, we have calculated y naught uh, as s bar into the given expression, and when s equals to 1 plus s into the given expression. So after calculating this part, we came to a this expression, which is given in one of the option, and similarly we did it for y1. When s equals to 0, y1 was this. When s equals to 1, y1 was this. So we calculated s bar into the given expression plus s into the given expression. And it was quite simplified by default. So we get to know that this is the y naught and this is the y1, which is the option number C. So you can note it. I'll wait for 2 minutes now. Now the second part, yeah. Okay, so let's proceed with the next question now. This is again a interesting question. So it says in a given circuit, the output can be given as. So it is asking for three properties when x is greater than y, x is greater than x is less than y, and when x is equals to y. So in the initial part of the circuit, what is given? It is a 4-bit 2's complement subtractor, and the output of the subtractor is given to this combination logic. So according to the subtractor and combination logic, there are certain things that we need to be aware of. For x greater than y, there are certain conditions. The conditions are Cout should be 1, and either of S3, S2, S1, and S0 should be 1. So this is a condition for x greater than y. For x equals to y, what is the condition? Cout should be 1, and all of S3, S2, S1, S0 should be 0. And for x less than y, the condition is Cout should be 0. We don't care about these initial these sum bits, but what we all we need to do is to check is Cout should be 0 in this case. So if I try to write the expression for x greater than y, x greater than y is nothing but Cout should be 1, so it should be ended with another condition. So Cout should be 1, and either also either says that it is a or in operation. So x greater than y will get the output which is the first output. So it will be nothing but Cout into S1 plus S2 plus S3 plus S0. Now for x equals to y, we have just written that Cout should be 1 and all of this should be 0. So it will come only if we take the bar of all of these terms. So it will only come 1 when all of these should be 0 and Cout will be 1. Since the bar of 0 will be 1, so it will only come out as 1 output when all of these are 0 and Cout is 1. So we can write for x equals to y, Cout S1 bar, S2 bar, S3 bar, and S0 bar. Same is the case with x less than y. X less than y implies just Cout should be 0, so it is nothing but Cout bar. So now we'll check the options. So Cout bar is in these three options. Then it is in these three options and this. So the correct answer to this question is option number B. You can note down the questions. The solution is here. Yeah. So you can note down the solution. I'll give you 2 minutes. So we can proceed to the next question. The next question says that the gray code of this number is denoted as x. So x is nothing but the gray code of 125 to the base 8. So it says that when we feed x to a binary to octal converter, then that octal number will be what? So first, we need to convert this given code into the gray code. So we know that first we will do the octal to binary conversion. So if we try to write 125 to the base 8 into binary, so it is nothing but 1 is 0, 0, 1, then 2 is 0, 1, 0, and then 5 is 1, 0, 1. So now we'll change it to gray code. So in gray code, what we do is we keep the first bit same and then we start doing the XOR of the consecutive bits. So 0 XOR 0 is 0, 0 XOR 1 is 1, then 1 XOR 0 is 1, then 0 XOR 1 is 1, then 1 XOR 0 is 1, then 0 XOR 1 is 1, then 1 XOR 0 is 1, and then again 0 XOR 1 is 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So it has, yeah, 9. So the gray code of this number is this. Now what it is fed into a binary to octal converter. So again what we'll do, we'll make a pair of 3, 3 and then 3. So it is nothing but 1 and then 7 and then 7 to the base 8. So the correct answer to this question is option number C. I hope it is clear. It is quite a basic question only. So correct answer is option number C. In the last question, the correct answer was option number B. Yeah. So take your time to note this. Yeah. This was quite a basic question in which we required a binary to gray conversion and then a binary to octal conversion. So I'll give you 2 minutes, then we'll proceed to the next question. Okay, we shall proceed now. So it is okay. So it is a IC 7485 question. We need to know some basics of IC 7485. So it is this IC is nothing but a 4-bit magnitude comparator. You just need to know that this IC 7485 is nothing but a 4-bit magnitude comparator. So now question is we need to compare two 128 bits. So since it is only a 4-bit magnitude comparator, so we need to check that what is the amount of iteration that is required. So it is nothing but 32. So 32 ICs will be required to check X and Y comparison. So the correct answer to this question is nothing but option number B. It was a basic question in which you need the knowledge that this IC is nothing but a 4-bit magnitude comparator. And since it is a 4-bit magnitude comparator, so it is asking to compare 128 bits. So since only one IC will cover 4 bits, so we need to check how many ICs will cover this 128 bits. So we need to divide this 128 by 4, which will give 32 as the answer. Again, I'll wait for 2 minutes. Okay, so we shall proceed now to the next question. It is again an interesting question. So it is given in the question that there is a multiplexer and there is a certain output Z which has been asked. So which of the following expression correctly matches the output Z? So it is asking Z in terms of either it is A greater than B, A less than B, or A equals to B, or A not equals to B. So we'll check that where this one is given in the Z, so that will be the output. So one is given in this bit 0, 0, 0, 0, then 0, 1, 2, 3, 4, 5. 5 is nothing but 0, 1, 0, 1. Then 6, 7, 8, 9, 10. 10 is nothing but 1, 0, 1, 0. And then 11, 12. So last is 15, 1, 1, 1, 1. So Z equals to 1 when, so let's take this bit as A1, A0 and then B1, B0. When A1, A0, B1, B0 is 0, 0, 0, 0. Then when A1, A0, B1, B0 is 0, 1, 0, 1. Or when A1, A0, B1, B0 is 1, 0, 1, 0. Or when A1, A0, B1, B0 is 1, 1, 1, 1. So if we check, so this A1, A0 represent A, and then B1, B0 represent B. So if we check for all the cases, Z will be equals to 1 when this and this are equal. 0, 1 is equals to 0, 1, 1, 0 is equals to 1, 0, and then 1, 1 is equals to 1, 1. So in all the cases, A1, A0 is equals to B1, B0, if you can see clearly. So the correct answer to this question will Z will be 1 when A is equals to B. So the correct answer is option number C. I'll repeat again. So it is given that Z equals to 1 and the terminals connected are 0, 0, 0, 0, then 0, 1, 0, 1, 1, 0, 1, 0, and then 1, 1, 1, 1. So these are nothing but the bits A1, A0 compared with B1, B0. Same is the case with all of these. So we just got to know that A1, A0 is always equals to B1, B0, or A1 is equals to B1 and A0 is equals to B0. If we write it together, then A is equals to B. So the correct answer to this question is option number C, which says Z equals to 1 when A is equals to B. Yeah, you can note down the solution. I'll give you 5 minutes. Okay, so we shall proceed now. Okay, so in this question, so this is a earlier question, so this is not a Simon 6 question, but still I'll try to cover it because it was asked as a doubt by some students. So this question says that the following circuit, the propagation delay of multiplexers is 1 nanoseconds, and then NOR gate is 1.5 nanoseconds, and then inverter NOT gate is zero point 0.5 nanoseconds. So it says that when PQRST are applied at the same time, what is the maximum possible propagation delay? So there are only two cases based on the select line. So either t is equals to 0 or t equals to 1. So if I try to cover the t equals to 0 case first, when t is equals to 0, this here it will be 1 and here it will be 0. So this will work and this will work. So if I try to make the circuit out because they have been applied at the same time, so this will work, and then from this mux the circuit will work like this. And if I use some different pen for when t is equals to 1, so this will be 1 and then this will be 0 since this is an inverter. So this will be 1 means this will work first, the NOT gate, then through the mux, the 0 part will work of the mux, and then y will get the output as y. So if I try to cover the t equals to 1 part, then propagation delay is, or we can write it as tau PD. It is nothing but the NOT gate propagation delay, the mux 1 propagation delay, the NOR gate propagation delay, and then the mux 2 propagation delay. So this will be nothing but zero point 0.5 plus mux 1 is 1 plus NOR is 1.5, and then mux 2 is again 1. 2 plus 2. This will be 4 nanoseconds. So we'll check when t is equals to 0. This was with a different color. I'll use this. Yeah. So when t is equals to 0, the propagation delay is the NOR propagation delay here, then the mux 1, and then there is no part, and then the mux 2. It will be nothing but 1.5 plus 1 plus 1, which is 3.5 nanoseconds. And here it is 4 nanoseconds. So the maximum possible propagation delay has been asked in the question. So the correct answer to this question is option number B. I hope it is clear. It is quite basic. You just need to be familiarized with the combinational circuit and how they work. And in this question, how mux work. So I'll give you 2 minutes to note down the solution, then we will proceed to the next question. The correct answer is option number B. Okay, so let me summarize what we have done till now. So this is the basic circuit of a magnitude comparator. We checked what will the condition according to the question. So, and this was a theoretical question. This was a quite interesting question in which we read about this ALU block and what can be the different expressions that we can make out of it. So we made out the expression of y naught and y1, y naught and y1, and we calculated the expression as asked in the question. And then we covered a combination logic question, which was a magnitude comparator question. So there were few conditions regarding that, and we made out the logic out of it. And we got the answer as option B. Then we did some conversion from binary to octal or from binary to gray. So first we converted this octal number to a binary number, then binary to gray, and then this gray code has been converted since it is a code in binary which was converted to finally octal. So the correct answer to this question was option B, C. And then we read a basic thing that this IC7485 is nothing but a 4-bit magnitude comparator. So to compare 128 bits, we require 32 such ICs. And then a simple mux question in which certain outputs were connected to one, and we checked that in for all the cases what was there, a1 a naught was always equals to b1 b naught, as you can check. We got to know that the output z will be high when a is equals to b. And after that we covered a simple mux question in which what was there, in which we need to calculate the propagation delay, maximum propagation delay. We calculated for both the cases. One case was this, and the second case was this. We got to know that the maximum that we can get is 4 nanoseconds. So the option B was the correct answer. So now we'll proceed to the next question. So it says that gray code of 567 to the base 8 and B74 to the base 16. So you need to be quite careful reading these notations. So one is a octal number and one is a hexadecimal number. So again we'll do the same thing as we did in the last part. So 567, first we'll convert it to binary. 5 is nothing but 101, and the 6 is nothing but 110, and the 7 is nothing but 1. Oh, okay, wait. 111. So this is a binary conversion. Now we need to convert it to the gray code. In gray code, what we do is we leave the first bit as it is. Then we'll do the XOR of consecutive bits. So 1 XOR 0 is 1, 0 XOR 1 is 1. Then 1 XOR 1 is 0, 1 XOR 1 is 0, 1 XOR 0 is 1. Then 0 XOR 1 is 1. Then 1 XOR 1 is 1. 1 XOR 1 is 1. Oh, sorry, 0 and 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Let me recheck. 1 is as it is. 1 XOR 0 is 1. Then 0 XOR 1 is 1. Then 0. Then 0. Then 1. And then 1. Then 0. And then 0. Yeah. So let me rewrite it. 1, 0, 0. 1, 0, 0. So now I again convert it to the octal number. So it will be nothing but 7. This is 1. And then this is 4 to the base 8. So the octal conversion of 576, the gray code of 576 to the base 8 is nothing but 714 to the base 8. So we have eliminated option A and option C from the options. Now we'll try and do the same approach with this B7416. So B is, we know, in the hexadecimal 9 and then A and then B. So A is 10, B is 11. 11 is nothing but 108 plus 2 plus 1. B is nothing but 1011, then 7 is 0111, and then 4 is nothing but 0100. I hope it is clear. So now we'll change it to the gray code. So we'll leave the first one as it is, then 10 XOR is 1, then 01 is again 1, then 11 is 0, then 10 is 1, then 01 is 1, then 11 is 0, then 11 is again 0, then 10 is 1, 01 is 1, 10 is 1, then 00 is 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is a gray code, and then if I try to convert it to the hexadecimal again, so this is the thing, these four are the thing, and these four are the thing. So 8 plus 4 is 12, 14. 14 is nothing but E. Then 8 plus 4 is 12. 12 is nothing but C. And then 1110 is it is again E. So this is to the base 16. So the B7416, the gray code conversion is this. So it is option number B is the correct answer. I hope it is clear. It is quite basic. You just need some mathematics. Let me know if you have any doubts regarding that. I'll repeat the same, but it is quite basic. So what we are doing in this, we are first converting the octal to its binary equivalent. Then the binary equivalent is getting converted to its gray code, and then finally the gray code which is in binary is converted to its octal equivalent. So we got to know the correct answer to this question is option number B by few minor calculations only. I hope it is clear. We'll proceed in 5 minutes now. Till then, you can note down this solution. Okay, so I'll give you some interesting problem. Maybe if it will come in the later stage. Yeah, it will come in the later stage. So let's try to do this question now. It is again a theoretical question. So it says that which of the following statements are false? Again, it is saying it which are false, not true. So we'll again check for all the cases. So it says that XS3 code is both a sequential as well as self-complementary code. So this thing is true for the XS3 part. It says that in SKY code now B is represented by this one. We know that A capital A is represented by nothing but this one, and then this B is just shifted. This one when shifted to the left is the B. So this is also correct, and then this is also correct. The third option says that access 3 code is 0011 added to binary code decimal, which is the correct value. The allowed values are 0011 to 1111. So this 1111 is not correct. We know that access code is nothing but 0011 to 1100. Since this 0 is converted to 3 in access 3 and 9 is converted to nothing but 12, which is 1100. So 1111 is not a possibility. So option 3 is incorrect. Then gray code is unweighted code with unit distance. Gray code is always a one bit difference code. We know that gray code is a one bit unit difference code and it is unweighted. It is also reflected code, as by reflecting n minus 1 bit, n bit gray code can be obtained. So yeah, this statement is also correct. If I track option number 5, so it says binary to gray and gray to gray. So we have already covered it. It does not require XOR but require XOR gates. So option 5 is also correct. So from the option 3 and 5 are incorrect. And it has been asked which are false. So the correct answer to this question is option number B. This was a theoretical question which we covered. You can analyze it, and if you have any query, you can ask straight away. Sorry for the noise. Let me try to mute for a few minutes. I hope I am audible again. So, one thing more, I'll highly encourage the student to take part in this live sessions, as these questions are have some different types and approaches which will help you in passing your exam quite easily. So, you need to be present in the live sessions. That will help you in solving the questions in your examination quite easily, because these questions are not all from the assignments, but they are some different type of questions. So, once you will have the conceptual knowledge and the exposure to these types of question, you will able to solve every question in your examination quite easily. So I will request everyone, if possible, try to attend these live sessions. So I'll repeat again till what we have covered, and then we'll proceed to the next question straight away. So again, the first question was a magnitude comparator circuits, and according to the conditions given in the question, we found out the answer. Then the next question was a true-false space question, which contained some basic. This was the most interesting question, in which a ALU block was given, and we need to calculate what was the y0 and y1 according to the questions and the conditions given. So we got to know that according to the conditions, we got to know the answer of the expression of y0 and y1, which was option C. And then we covered a combinational circuit and then checked the conditions for x greater than y, less than y, and equals to y for the given question, which was nothing but these three conditions. And from these three conditions, we made out a certain logic, which was option number B in the question. So, and then we covered a binary to gray code, in which what we need is not binary to gray, octal gray code conversion. So For this, what we need is octal to its binary equivalent, then binary to its gray equivalent, and then gray, which is in binary to again its octal equivalent. So this is a cycle, kind of cycle. So we got to know that this is a gray code, and we converted it to the binary again. And option C was the correct answer to this question. Then we got to know that about this IC, which is nothing but IC7485, which is nothing but a 4-bit magnitude comparator. So for instance, we need to compare 128 bits, so we need to divide 128 by 4, so 32 such ICs will be required to compare the X and Y. Then again, we covered a interesting question which was a mux, which will be z equals to 1 when certain outputs were attached, and we got to know that whenever those outputs were attached, a1 a0 was always equals to b1 b0, from which we concluded that a is always equals to b. Then we covered assignment 4 problem, which was this year's assignment 4 problem, in which we needed to calculate this maximum propagation delay, which was quite interesting and easy. And then at the last, we covered this gray code of certain different outputs. This was 8 and then this was 16. So we covered this 8 and 60, and we got to know that this was the output. The gray code of this was nothing but 714, and the gray code of this hexadecimal was nothing but ECE. So option B was the correct answer to this question. And then the last that we covered was again a true false type question, and we got to know that option 3 and 5 are incorrect in this statement. 3 and 5 are incorrect. So option B will be the correct option, since it is asked that which of the following statements are false. Okay, so now we'll proceed to the next question, which says the output Y of a 2-bit comparator is logic 1 whenever 2-bit input A is greater than 2-bit input B. So 2-bit, so we have total 16 cases, so let's make them A1 A0 and then B1 B0. So if I try to write all of them, 3, 4, 5, 6, 7, 8, 3, 4, 5, 6, 7, 8, then 0. Okay, then 0, 0, 0, 0, 1, 0, 4, 5, 6, 7, 8, 0, 1, 0, 1, 0, 1, 0, 1. So we get to, okay, let's undo this last thing. So now we'll compare this A1, A0 with B1, B0. So we can check that it is given that whenever 2-bit input is greater than 2-bit input B. So when A1, A0 is greater than B1, B0. So it is asking for the number of such combinations which we can make from this 2-bit comparator. So we can check A is greater than 0 when A is 1, 1, and B is 0, 0, 0, 1, and 1, 0. And when this is 1, 0, so this is 0, 0, 0, 1. When this is 0, 1, then this is 0, 0. So there are 1, 2, 3, 4, 5, 6 such combinations. When A is greater than B. So we have written all those 6 combinations out of this total 16 combinations. And then if we write such expression for n combinations, so n bit magnitude comparator, so it will be when A is greater than B, the number of possible solutions are 2 to the power 2n minus 2 to the power n by 2. And the total combinations are 2 to the power 2n. So you can check, this is a 2-bit magnitude comparator. So when we take n equals to 2, For a greater than b, it will come as 2 to the power 4 minus 2 to the power 2 by 2, which is nothing but 16 minus 4 by 2, which is 12 by 2, and it is 6. So the correct answer to this question, we'll write it first, is 6. And the total combination I'll write again. It is 2 to the 2n, so for n equals to 2, it will be 16. And same is the case with a less than b. The same formula can be applied to the power 2n by 2 to the power n by 2. And the rest of the cases are a equals to b cases. So out of these 16 cases, 6 cases will have a greater than b, 6 cases will have a less than b, and remaining 4 cases will have a equals to b. So this is nothing but 2 to the power n. You can note down the solution. We'll proceed to the next question in 5 minutes. So the correct answer to this question is, again I'll write, it is 6. If you have any query, you can ask straight away. We'll do the next question in 2 minutes. Okay, so let's start the next problem. Again, this is an interesting problem. So it says two 2-bit numbers A1, A0, and then B1, B0, which is similar to the, are given its input to a 2-bit comparator. So there will be 3 cases: A less than B, A greater than B, and A equals to B. So now the output of this comparator PQR is connected to a 3 cross 8 decoder. So it is saying that what will be the probability that S2 is 1. So S2 is 1. We need to calculate the probability when S2 is 1. So yeah, so it is a 3 cross 8 decoder. So let me familiarize. U with this decoder. So it has three input for the given question. Let's say it is PQR and it has eight output. We start from S0, S1, S2, S3, S4, S5, S6, and then S7. So we know that S2 will be 1 when S2 is nothing but 0, 1, 0. So if I try to write in PQR S, then all the cases 0, 0, 0, 0, 1, 1, 1, 1, then 0, 0, 1, 1. So this is nothing but S0, S1, S2, S3, S4, S5, S6, S7. So this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, and then this is 7. I hope it is clear. So it is saying that when S2 equals to 1, what is the probability when S2 is equals to 1? So S2 is 1 when this P is equals to, you can see clearly see, is 0, Q is equals to 1, and then R equals to 0. And we know that Q is what? A greater than B. So we know that for a 2-bit, we have covered it in the last question only. If we check the cases when A is greater than 0, so for 1, 1, there will be three cases 0, 0, 0, 1, and then 1, 0. For 1, 0, there will be two cases, and then for 0, 1, there will be 0, 0. So there will be total six cases out of how many cases? Total combination we just calculated, which is 2 to the power 2n. So this is nothing but 16 combinations. So the probability, if we say when S2 is equals to 1, so there are total six cases when S2 will be 1 out of the 16 cases. So if I try to do some maths, so this will be point, then 3, then 67, and then 5. So the correct answer to this question is nothing but 3 by 16, which is 0.375. We can mold this question to some different, which is, let's say, 0, 0, 1, which is, let's calculate the probability when S1 is equals to 1, and let's calculate one more probability when S4 equals to 1. So you need to calculate these two. I'll give you 2 minutes if you can calculate, then I'll repeat the same question. So I've calculated for S2, you need to calculate it for S1 and S4 if you can. I'll do it in 2 minutes. Okay, let me try to do it. So, wait a bit. So let's say for S1 equals to 1. S1 equals to 1 means, I'll cover here, yeah. So S1 equals to 1 means when R equals to 1 and rest of the P and Q are 0. So R equals to 1 means when A is equals to B. So for A1, A naught is equals to B1, B0. So there are only four cases which will be 0, 0, 0, 0. Then 0, 1 will be 0, 1. Then 1, 0 will be 1, 0. And then 1, 1 will be 1. So total four possibilities are there for total 16. So the answer to this will be 1 by 4, that is 0.25. And similarly, if I try to do it for S4 is equals to 1. So S4 is nothing but 1, 0, 0. You can check here. So that means when P is equals to 1 and Q and R are 0. So this covers what? When A is less than B. So A is less than B, 0, 0 for three cases of B, 0, 1, 1, 0, and then 1, 1. Then 0, 1 is less from 1, 0 and 1, 1, and then 1, 0 is less for 1, 1. So again, there are total 6 cases out of the 16 cases. So again, the answer will be 0.375. So we calculated for P S2 is equals to 1. This will be the answer. For S1, the answer will be 0.25, and for S4, the answer will be 0.375 again. So we have covered three questions in a single question, and this was a quite interesting question. So you should look to it quite carefully. So for the three parts, the answers are 0.375, 0.25, and then again 0.375. So you can note down the question. We'll do the next problem in 2 minutes. Okay, this was quite an interesting question. Please look at it quite carefully whenever you see the recording. So now we'll again cover a basic question. So now what this question says, it requires some knowledge of adder, half adder basically. So we know that for a half adder, sum is nothing but A XOR B, and sorry, carry is nothing but A into B. So it says in the following circuit diagram, what are the values of S2 and C2? So in the given circuit here, S1 will be nothing but A XOR B, and C1 will be A into B. So this is getting ended, and the same, let's say Y is getting to both the half adder. So let me calculate Y. Y is nothing but S1 into C1, which is A XOR B into AB. So if I try to open it, this is nothing but A bar B plus A B bar into AB. If I try to further open it, it is A bar B plus A B bar B. So we know that x into x bar is nothing but 0, and 0 multiplied with any variable is 0. So A bar is 0, into B will be 0, and then again 0 plus 0 will be 0. So in this half adder, what we are getting is 0 and then again 0. So we know that S2 will be nothing but 0 XOR 0, and C2 will be 0 into 0. So both S2 and C2 will be 0. So the correct answer to this question is option D. I hope it is clear. It is again a quite basic question. If you have any doubt, you can ask straight away. We shall start the next problem in 2 minutes. Please note down the solutions. So let's start the next problem. Okay, so now we are coming to the code's error detecting and error correction. So it says that Hamming code is one of the code which is used to detect and correct errors. So it says we need to find the 12-bit Hamming code for the given data word. So data word is nothing but a 8-bit data word, and we have a 4-bit, a 12-bit Hamming contain 8-bit of data word and 4-bit of parity. And the sequence is to this 12-bit data code is nothing but P1, P2, then D1, P3, this is D1, P3, then D2, D3, D4, then P4, then last 4-bit D4, D5, D7, D8. So we have given the data bit is nothing but 101000. So this is nothing but D8, D7, D6, D5, D4, D3, D2, and then D1. So we can write straight away that D1 is, let me use some different pen. D1 is nothing but 0, then D2 is 0, then D3 is 1, then D4 is 1, then 0, 1, 0, 1, 0, 1, 0, 1. So we need to calculate these four parity bits. So for this, we have a certain relation. So parity 1 is 1 when more than one bits are there. So we need to calculate XOR of 3, 5, since it has more 1, 5, then 7, then 9, and 11. So if we try to XOR the bits, so 3 is 1, 1 XOR with 5 is 0, and then 7 is 0, and then 9 is okay. So this is 0, 1. I have written something wrong, I guess. 3, 5, 7, 9, and then 11. So 11 is P2. This will become 0, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. It will be 1, 1, then 1, then 0, and then 1. P1 will be 1. So let's check for D1 first. So D1 is 0. D1 is the 0, yeah. Because I have written the sequence opposite, I guess. D1, D2, D3, D4, D7, D8. Now D1 is 1, then D2 is 0, then D3 is 1, then D4 is 0, then this is 1, 1, 0, 0. So 1, 1, 0, 0 is present in all of them. Then D1 is 1, then D2 is 0, which is this. So this option is eliminated. Then D3 is 1, which is this. Then D4 is 0, which is this. Then we need to calculate these 4 bits. So I'll use some different pen. So this bit, this bit, this bit, and then this bit. So I'll write the relation for all of them. P2 is XOR of 3, 6, 7, in which uh, there is exactly same matching ones. Then P3 is XOR of 5, 6, 7, and then 12. And then P4 is XOR of 9, 10, and then 11, and then 12. So once you will check, you'll come out that this is 0, then 0, 1, 0. So this will come out to be 0, this will come out to be 1, this will come out to be 1, and this will come out to be 0. 0, 1, 1, 0. Yeah. So the correct answer to this question will be option B. So you need to check the manual calculations. So when once you will do them, the XOR of these corresponding things, it will come out that P1 is nothing but 0, P2 is nothing but 1, P3 is nothing but 1, and then P4 is nothing but 0. So the correct answer to this question is option B. You can note down the solution. We'll start the next question in 5 minutes. You can check it by yourself also. You can try this question. This is a basic question which just requires the knowledge of the basic Hamming code equation. So it says that how many check bits are required for the data worth of 25 bits. I'll try to write the equation, maybe that will help. So the basic condition is for k bits when 2 to the power k is nothing but m plus k plus 1, and these m is the data bits. So you can try for different calculations or different combinations of these. Maybe you can check which of the following is a minimum number which is satisfying the following given question. So start with the minimum bit and then go towards the highest bit. We always look for the minimum bits in the Hamming code since lesser bits means lesser computational time and lesser circuitry involved. So let me try it for k is equals to 4. K is equals to 4 means 22 to the power 4 when is greater than m is 25 plus k is 1, k is 4 and then 1. So 2 to the power 4 is nothing but 16 is greater than 30. So this is not true. So k is equals to 4 is not the answer. So similarly, you can check for k is equals to 5 also. 2 to the power 5 is 25 plus 5 and then 1. So this is nothing but 32. 32 is greater than equals to 31. So yeah, this is satisfying. So the minimum bit is always the answer. So the check bits required for the given 25 bits data word are nothing but 5. So the correct answer to this question is option B, which is 5. You need to just make aware of this relation. This is a very important relation regarding Hamming code. So since lesser students are attending these sessions, so there is no time in between to let you do the questions by yourself. So that is why I'm continuously solving the answers and by myself. So I hope you understand. So that is why the session time is reducing a bit for the whole 2 hours. So I'm doing the questions continuously. So please try to see the recordings, and if you have any doubts, you can contact me anytime and the respective TAs and the professor of this course. You can note down the solution. We'll do the next question in the 2 minutes. Okay, so we'll proceed now. Okay, so this is a basic theoretical question. So it says the code used to reduce error due to ambiguity in reading. So let me make you familiarize with all these types of code, which is in the next. So remember that to remove error or ambiguity, we always prefer gray code. I'll tell you the reason why. So by looking at this, so you can see that in the binary, there is a more than one bit change in the consecutive code. So for one, it is 0011, and for two, it is 0010. So 01 is getting changed to 10. So which is more prone to error. So there is a 2-bit change. Same is the case with octal. You can see that here 001 is getting changed to 010. And then here also this one, let me, yeah, this 01 is getting changed to 10. So again in accessory also there is a 2-bit change, and in octal also there is a 2-bit change. So once you'll check for gray code, what you'll notice is there is always a maximum of 1-bit change in each and every consecutive bit. So you can see there is a 1-bit change here, then there is a 1-bit change here. Then if you check here, there is only a 1-bit change. Then if you will check here, there is only this and this bit change. Then again, this bit and this bit is getting changed. And if you'll see here, then this bit and this bit is getting changed. And then this bit and this bit is getting changed. So in gray code, the maximum change in bit for consecutive decimal values is always 1, which makes it less prone to errors. Sorry. And superior to other codes such as binary, BCD, octal, XS3. So the correct answer to this question is nothing but gray code, which is option number 3. So I'll try to repeat again. Gray code is always used to reduce the error due to ambiguity because of its 1-bit change in the consecutive decimal digits. In having code, you need to get familiarized with this code, with this condition, which is nothing but 2 to the power k is always greater than m plus k plus 1. Then again, the parity, you need to know the sequence of it. Then this is was wrong. This was the correct sequence, and then you just need to calculate the parity bits by the following relations. Okay, they got removed, so I'll write it again. So P2 was nothing but XOR of 3, 6, 7, 10, 11. Then P3 was nothing but XOR of 5, 6, 7, 12. And P4 was nothing but XOR of this 9, 10, 11, 12. Once you calculate it, it will be nothing but even P2 is 0, 1. Yeah, so it will be 0, 1, 1, 0. Then this was a interesting question. S1, C1 when they are getting same, so after XOR they both were getting 0. So sum and carry both will be 0. Then this was again a nice question of decoder. Yeah, this was quite a unique question. So you should do it by yourself also. I calculated for three cases. You can also calculate. So for the first case, you can calculate by yourself. Then for the rth case, you can calculate. Then this the general relation. Okay, let me for a greater than b and a less than b also. This will work, and the total combination is nothing but 2 to the power 2n. So you need to learn these relation. Then this was a nothing but a statement based question. This was a gray code question which requires a conversion. This was a assignment 4 question, which was quite interesting and easy to do. Then again a mux question. We got to know that whenever we are getting one, A is always equals to B. Then IC 7485 is nothing but a 4-bit magnitude comparator. So we need 32 such ICs to compare 128 bits. Then again there was a conversion question, and then this was a question we got to know the condition for all of the three cases, and we write the logical expression based on that, and we got the answer. Then this was a most interesting question which contained a ALU block, and we calculated the corresponding y naught and y1 according to the question, according to the conditions given in the question, and we got to know that option C is the correct answer. Then again a theoretical question, and this was a magnitude comparator circuit in which we got to know that f1 is nothing but when y is greater than x, this is when y is equals to x, and this is when y is less than x. So the question says that y is 1 and x is 0. So y is greater than x, so we need f1 to be 1 and rest of them as 0. So this was all from the combinational circuit part. So you can see that till week 6, from 1 to 6, we have covered the combinational circuit, and in the upcoming weeks, we will be covering the sequential circuits. This is the backbone of digital electronics. This will be asked in most of the competitive exams such as GATE, ESE, etc. So you need to be quite attentive, and you should attend these live sessions quite properly because this is the main content of digital electronics. So it is quite important. Especially week 7 is quite important because it will cover the basics of all the sequential circuits, and what is a sequential circuits, what how it is different from a combination circuit. We'll get to know uh, a tidbit about it. So please try to attend the live lecture of all these upcoming weeks because sequential circuit is one of the most important one of the most important topics in this digital electronics. So with this, we can wrap up the session for today. If you have any doubts or any query, you can ask me anytime. I'm always available. Maybe you can even email me. I'll write the email. So you can email me at this address. So it is nothing but singhal dot 6 at the rate iitj dot ac dot in. If you have any query, you can reach out to me, and you can reach out to the NPTEL. We'll try to figure out and solve your query as soon as we can. So with this, we can wrap up the session for today. It was great taking the session. Please watch the recording. I hope it was helpful, and let's meet in the next week on the assigned time slot, which was Monday 6 to 8. So let's meet next week, Monday. Thank you for attending the session. Let me stop the recording. So we'll meet next week, Monday. See you till then. Try to solve the problems of the combinational circuit, and all the best for your exams, upcoming exams. I hope you will score well and do well in your examinations. Thank you.